Well, hello everybody. Welcome to the last chapter in the meteorology section, chapter 14, weather patterns and severe weather. The learning objectives here are to understand air masses, know how they're classified and the general weather associated with each type, know what a front is and how warm fronts differ from cold fronts, be able to explain the primary weather producers in mid-latitudes and the weather patterns associated with them. And that primary weather producer is called a mid-latitude cyclone. So we know it's going to be a mid-latitude low pressure system. Don't let that fool you. It's a traveling low pressure system that also has high pressure attached to it. And explain the atmospheric conditions responsible for thunderstorms, tornadoes, and hurricanes, and classify the severity of hurricanes and tornadoes. So air masses, that's what we need to concentrate on here at the beginning. An air mass is this big body of air, a big mass of air, if you didn't know, a big mass of air that has certain temperature and moisture characteristics. The strange weather patterns that we have here in mid-latitudes, the changeable weather patterns that we have in the mid-latitudes are because of these air masses that move in and out of a region on a regular basis. So when an air mass moves out of its source region, it will start taking on the characteristics of that new area that it's moving through. So it might have started out in a cold region, but it moves into lower latitudes where it's warmer, then that air mass is going to pick up the characteristics of that warmer area. So an air mass has to come from a source region that has dominant temperature and moisture characteristics. And it has to stay in that area for a long enough time in order to pick up those characteristics. So this is what we mean. We have these cold, dry air masses that start out over northern Canada at a very low temperature. And then as it moves south across the US, you see how the temperature goes up. I mean, it's still going to be cold, but the temperature increases slightly as it moves into these lower latitudes where the temperature, where there's more solar energy reaching these places. So if it went further south, it would end up being even warmer. So how do we name these things? The source region is where the air gets all of its characteristics. So we use a little m and a little c to refer to the moisture characteristics. M stands for maritime. A maritime air mass is going to be humid. It's going to have water vapor associated with it. And the source region, as we learned a long time ago, maritime means all things water. So the source region is going to be over water. The C, the little c, refers to continental, and that's a dry air mass. The source region is going to be over land. Capital P and T refer to the temperature characteristics. P is for polar, cold. Source region is high latitudes. T is for tropical, warm to hot, and the source region is going to be in low latitudes. There are also E, equatorial. We never are influenced by equatorial air masses, but they are out there. We put these two letters together and we get the designation for the different air masses that impact us here in the US. Little c, big P, continental polar. So continental polar air is going to be dry and cold. CT, continental tropical, is going to be dry and warm. MP, maritime polar, is going to be moist and cold. And MT, maritime tropical, is going to be moist and warm. So these are the areas of the US, or areas of North America, where we have these air masses with these particular characteristics. Let me grab a pen here, as I usually do and mess up. Let's do green. So for us here in California, in the wintertime, Did it not do? There we go. In the wintertime, these are the air masses, these maritime polar air masses that are breaking out of that semi-permanent low pressure that sits up here in the wintertime. Do you remember what the name of it is? It's the Aleutian Low. These air masses are unstable when they reach us, so we end up getting some weather that we'll talk about a little bit later. Maritime tropical air masses are moist and warm, and we see that those can influence interior into the Great Basin, usually during those summer monsoon seasons. CP air from northern Canada, CP air from central Canada that comes down, drops down into the US. Maritime polar, those air masses break out of that semi-permanent low pressure system that sits over here in the eastern side of North America. And if you remember the name of that, it's the Icelandic low. So these storm systems break out of that, and that's why we get the stormy weather that we have in the northeastern part of the US in states like Maine and New Hampshire and Massachusetts and into New York. Then maritime tropical air is responsible for the muggy, hot conditions that we have in the south during the summertime. Continental tropical air, that is dry and warm air, and you can see how it influences the interior in these interior desert regions of the Great Basin and into the portion of the western high plains region of the US. So the MP air masses that influence the western states start out as continental polar air masses over Siberia. So they start out and with completely different characteristics than they end up with by the time they get to us. As they cross the Pacific, they pick up moisture, and that can get dumped out on us. And then here in California and the Washington and Oregon, we get that orographic effect. So we end up with rain normally in the valley, and then as that air continues to rise over the Sierra, it adiabatically cools, the temperature goes down, there's still moisture locked in these air masses, and they end up getting snow. Maritime polar air from the North Atlantic impacts these storm systems and are responsible for these storm systems that we call nor'easters. Nor'easters are kind of like hurricanes, except they don't have an eye, but the effects can be just as wicked as with a hurricane. CP air from Canada can result in these lake effect snows in areas along the Great Lakes. If you've ever watched football in the wintertime, and especially Buffalo, New York, always snowing, and usually those are lake effect snows. And then the MT air from the Gulf of Mexico results in hot, sultry, rainy conditions in central and eastern states. So this is how the air masses change as they head to us in the west. Start out over here in Siberia as very cold and dry, get modified as they move out, as the air masses move out across the North Atlantic. They're still going to be cool, but they pick up that moisture. And these are areas that are famous for their lake effect snows. Let me get the laser pointer here. On the lee side of these lakes, so Marquette, Wisconsin, or sorry, that's Marquette, Michigan, sorry about that. Leeward side here of Lake Michigan, leeward side here of these lakes. Those are the snow belts, and this is what can happen with these. This is one lake effect snow in upstate New York in 2004. Pretty deep. Here's a nice satellite image that illustrates what's going on. Here's Canada up here in the north, to the north of the lake. These splotches of white, those are lakes that are covered in snow, but we see that it's clear here. There's no cloud cover at all. But as these air masses move out and they move over these lakes, then there's a lot of moisture in those lakes, above the lakes. They pick that up and these clouds start forming, and then we get these really thick clouds over here. That's one of those lake effect snows. All right, so air masses then are these air masses that have characteristic temperature and moisture features in them. So a front is the boundary between unlike air masses. Unlike air masses do not like to mix. Air that is a different temperature, you have a warm air mass and a cold air mass, they're not going to meet up and mix. They stay separate because of the density differences. Why do we have the differences in density? Because the temperature is different. So it's along frontal boundaries that the major weather producer of the mid-latitudes, called a mid-latitude cyclone, this is where they are formed. This is the symbol on a weather map. This would be the symbol for a warm front. This indicates that the warm air is, if you see how these little semicircles are on the line, that means that the warm air is moving from this direction to this direction. So the warm air is moving from the south to the north. The semicircles are pointed in the direction that the warm air is moving. This is a cold front. If you ever forget the difference between the two, or one way that I use, and that has kept me sane all these years, is looking at the triangles on the cold front. I just always think of this as sharp, biting cold. So the triangles illustrate the cold front. The way they're oriented here, the cold air is back here, and the cold front is moving this direction. Remember, this indicates, wherever this is located on the map, it indicates the front of the air mass. So this is the front of the warm air here. This is the front of the cold air here. Then we have these two over here. One of them is a little bit strange because we have the semicircle on one side of the line and the triangle on the other side of the line. This is called a stationary front. We have warm air back here, we have cold air here, and remember, they don't like to mix, so they're just kind of staring at each other. But that doesn't last very long because Earth is rotating, so there's going to be this dynamic motion that is going to take place. Then this one right here is called an occluded front. We have both the semicircle and the triangle on the same side of the line, and it's purple. If you're looking at a weather map that's in color, then the occluded front would be in purple. Well, okay, what happens at a warm front? We need to look at the weather conditions that are associated with a warm front and the weather conditions that are associated with a cold front. Warm air, with a warm front, warm air is coming into an area of cooler air. How do I know that? Because it wouldn't be called a warm front if it wasn't invading an area with temperature conditions unlike the warm front. So it's coming into an area of cooler air, shown on a weather map by a line with red semicircles on it. East of the Rockies, this type of air will enter from the Gulf of Mexico. It's less dense. Warm air has a harder time displacing colder, denser air. Cold air is heavy, dense, so it tends to sink. The boundary that separates these two is very gradual. Warm air has the tendency to rise, cold air has the tendency to sink, so this warm air slides in over the cold air. And as it slides in, it's higher and higher, it's going to adiabatically cool. And it will end up, we will end up with clouds forming in advance of the arrival of the warm front. At the warm front itself, if we move closer and closer to where the warm front is, then we would tend to have light to moderate precipitation. This is what we're talking about here. So 2 to 3 days ahead of the warm air actually coming into that area, pushing out that colder air, cirrus clouds would be the result. The air is moving upward, it's adiabatically cooling, and at these elevations up here, any water vapor is going to be frozen. So we have ice crystals forming the clouds. That means that they're cirrus clouds. If we were traveling in a car and we were traveling this direction, then we would see that those clouds start to thicken up and get a little bit lower, and now they're cirrostratus clouds. Moving on, we see that they're thickening up and getting even lower. They're altostratus clouds. Alto, middle height, stratus, layered clouds. Then as we get closer and closer to the front itself, the clouds get thicker and lower. They're now nimbostratus clouds, and we have light to moderate precipitation. And that might last for 2 to 3 days because the warm air is moving slowly. So we get totally different weather conditions along the path of where that warm air is sliding in over the cooler air. Cooler temperatures over here at the surface, and as we travel this way, and this could be hundreds of miles that we're traveling to get to the warm front, the temperature is going to moderate slightly until we cross over, we get out of the rain, we're over here, and now we're in that pocket of warm air. This is why weather is so changeable in the mid-latitudes. So that's a warm front. We could label the warm and cold air here in the blanks that have been provided for you. So I won't label them, but I will point them out. This is the area of cold air. If you didn't know that, it says polar air. So this is the area of cold air. The warm air is moving, come on. The warm air is moving this direction. So there's our arrow. The cirrostratus clouds are going to be in this area right here, cirrostratus and altostratus, and then the nimbostratus clouds are going to be in here, and this is the area where the rain would be most likely falling, and then over here, this would be the warmer air. So I would point out to you that we could have a warm front come through and we might not necessarily get any rain at all. We could have a cold front move through and we don't necessarily get a thunderstorm or a tornado. It just depends on the characteristics of the air that's already over us and how different they are from the characteristics of the air that's coming into us. So precipitation, as we said before, the precipitation can last for extended periods over large areas. Warm fronts can occasionally be associated with cumulonimbus clouds and thunderstorms. Overrunning air has to be very unstable, and the temperatures on the opposite side of the front must greatly contrast for that to happen. But after the passage of the front, there will be a gradual increase in the temperature because we are now being enveloped in a warmer air mass. All right, cold fronts. What about cold fronts? Cold fronts form when we have dense cold air that's moving into an area occupied by warmer air. Cold fronts move faster than warm fronts. So therefore, it has a very steep front to it, whereas the warm front had this nice, gentle, let me see if I can draw this here. Sorry that I have to keep always saying this, folks, but that's a flat slope. But warm front has a gentle front like that. Cold front would look like that. So it's moving fast. It advances into this area of warmer air, and this warm air wants to rise anyway. Warm air rises, cold air sinks. So it comes in and it wedges that warm air up very violently, and we end up with our violent weather maker cloud that can form, our cumulonimbus cloud. Remember, these things can grow up to the bottom of the stratosphere depending on how much water vapor is in them and how much of that water vapor is condensing and releasing that latent heat energy in the cloud. Never forget, latent heat energy is the fuel for how all these storm systems develop. And for these cumulonimbus clouds to get higher and higher, that means that condensation has to be taking place in the cloud so that it remains warmer inside the cloud than outside the cloud. So we can have these violent thunderstorms with these updrafts and downdrafts in them, with thunder and lightning and heavy winds, and then in extreme conditions, these things can spawn tornadoes. Tornadoes can really be spawned in any unstable weather condition, but they are quite common when we have these cold fronts pushing into these areas of warmer air. If we have this big contrast between the air being cold and dry and the air being warm and moist, and those are the ingredients that are necessary for tornado outbreaks. After the cold front passes, the temperature drops and the pressure rises. As the temperature drops, that means that the air is going to be heavy and cold, so it's going to be sinking. Sinking air is stable air. Sinking air is stable air. We don't have uplift going on, so high pressure is characterized by no cloud cover or very little cloud cover. So this is the diagram for a cold front moving into an area. Here's that steep front, that steep face of the cold air, pushing in quickly to this area of warm air. So the warm air gets violently, excuse me, violently pushed upward, and condensation can take place, and we end up with cumulonimbus clouds. This is typically what we see when we're listening to a weather report of a cold front moving into an area. What you're seeing is a line of thunderstorms here. This is the cold air coming in from this direction. There was warmer air here, so it's pushing it up, and we see a line of thunderstorms. The good thing with these, because they're moving so fast, the storms come and then they move somewhere else. So Woodland has had some thunderstorms. They're headed to Sacramento, and then this is when you'll hear the weather reports saying, yes, Elk Grove, you need to watch out within the next hour or two because this line of thunderstorms is headed toward you. Remember, with thunderstorms, there's lightning. You would not have thunder if you didn't have lightning. And here's the cross-section view of it, the advancing cold air behind the cold front. Then once that passes, we're in this pocket of colder air back here. High pressure, sinking air, descending air is stable. We have uplift over here, so this is where all the nastiness, all the nasty weather will take place. So label the zones of warm air and cold air. Well, this is cold air back here. This is the warm air out here. The direction of motion of the warm air, well, we drew the arrows. It's being uplifted. And cumulonimbus clouds would be expected in this region right here. And label the areas of the most intense storm activity here. Sometimes the cold front can be so fast that it pushes air out ahead, way out ahead. So you can have a line of thunderstorms that are in advance of the actual front of the cold front. So this is the type of cloud that we're talking about. That's a cumulonimbus cloud. Remember, when we get this flattened out look to it, that means that the temperature inside the cloud is equalizing with the temperature outside the cloud. But if it's still being forced upward, it will grow horizontally rather than vertically. But as long as the air is warmer inside the cloud than outside, warmer, cooler, that's supposed to be a C. As long as it's warmer, it will continue to grow ever upward. And inside this cloud, what's causing it to grow are these updrafts. Those updrafts are warm, but as they get higher and higher in the cloud, they cool down. So we have these downdrafts. Then they will warm up as they get closer to the surface, and then we have more updrafts. It's just a series of updrafts and downdrafts, and these are violent, very violent. So low pressure systems then come in different types. The mid-latitude cyclone is the largest one in size. It can impact half the country. Thunderstorms are low pressure systems. Tornadoes are the smallest of the low pressure systems, but they can be the most deadly. And then hurricanes or tropical cyclones are close second in size to mid-latitude cyclones. So all of these low pressure systems. The first one that we'll talk about are the mid-latitude cyclones. Primary weather makers in the mid-latitudes, large centers of low pressure traveling from west to east. The largest weather contrasts occur in spring, so that's when we usually have the most violent weather associated with these moving systems. Get a lot of tornadoes. Just the other day, there was a tornado in Jonesboro, Arkansas. And we've had many tornadoes over the course of the winter months here and into spring. So the weather will change in places. Let me say that again. The weather changes that an area will experience will depend on the path that the storm is taking. The model of mid-latitude cyclones was developed in the early 1900s by Norwegian meteorologists. Remember the Bergeron or the supercooled droplet theory and rain formation? That came from the Norwegian School of Meteorology too. Norway is a Scandinavian country, and they experience lots of storms. They're fishermen, they're shipbuilders, so it really was to their advantage to understand how storms form. So they laid out the first theoretical groundwork on figuring out how these systems move and how they develop. And the terms themselves, fronts, they likened these cold fronts and warm fronts to warring armies. So all this was going on when World War I was going on, where you had different countries that had different battle lines. So they would talk about the German front or the British front or the US front. So that's where those terms came from for cold fronts, occluded fronts, stationary fronts, warm fronts. This is what one looks like here. They're also called wave cyclones. So let's track the development of one of these from the Pacific Northwest and as it moves. This storm track that you see here, that is steered by the jet stream. The storm track depends on how the jet stream is moving. So up here, it starts up here. Well, actually, it could start anywhere. Wherever you find these two unlike air masses that are meeting up, you can get a mid-latitude cyclone that forms. So this is a likely place for two unlike air masses to meet up. So you see what you have here, a stationary front where there's warm air pushing from down here and there's cold air pushing from the north. So warm air moving up from the south, cold air pushing down from the north. But there are other regions here where we could get these developed. Remember the MP air up here and the MT air here, so they can meet up. CP air coming from Canada can meet up with the MT air here, so this is a really good region. And in fact, this area is known as Tornado Alley because of the frequency of tornadoes that they have, because of this cold, dry air dropping down from Canada, encountering this warm, moist air, or this cold air coming in from over the Rocky Mountains, meeting up with this warmer air coming up from the Gulf of Mexico. This is just a breeding ground for violent weather in here. So what happens over the course of a few days, this is going to start changing. We know that there's lower pressure involved. So where is the low pressure? Is the low pressure going to be associated with this warm air coming up from the south or this cold air pushing down from the north? And you know, I hope you know by this time where the lower pressure is going to be. It's going to be in the warm air mass, that less dense air that's moving upward. Cold air is heavy and dense, so it's going to be associated with high pressure. So in a low pressure system, we know that it rotates counterclockwise. We know that the Earth rotates. We know that Coriolis is going to come into play. This air begins to move out, and there's a bend or a little kink in it where there's the area of lowest pressure, and the air would be moving like this, coming down from here, coming up from here, and then around this way. So there's the area of lowest pressure. The air is moving counterclockwise. Remember, counterclockwise motion in the low pressure system in the northern hemisphere. In the southern hemisphere, it rotates clockwise because Coriolis is different in the southern hemisphere. So at this point right here, as it's moved, it's fully developed mid-latitude cyclone, or because it looks like a breaking wave, wave cyclone. So we still have this motion this way, if you follow my arrows. All right, the warm air is moving faster than the cold air. So at some point, that cold air is going to catch up to the warm air. And the easiest place for that to happen is where it has the least distance to travel, and that's right in the apex of the wave. So the cold air is caught up with the warm air here, and look what kind of a front we have now. We have an occluded front. And as it continues to move, more and more of that cold air is going to catch up to the warm air and give us an occluded front. Here it's still fully developed. Wherever this is, depending on where you're located in relation to the occluded front, in front of the warm front, behind the warm front, in front of the cold front, behind the cold front, your weather is going to be different. And that's why the weather varies so much from day to day here in the mid-latitudes, especially in the United States, because we have a huge area that is these mid-latitude cyclones dominate. So we are a country that has some of the most variable weather in the world. And this is a daily weather map, and we see a lot of stuff going on right here. Here we have one of those stationary fronts forming up here. Here we've got this cold air coming down from Canada, so that's a cold air pushing into areas of warmer air here. Here's a big old line of a cold front, I should say, a big mass of cold air coming in here. There's our warm air. So there is a fully developed mid-latitude cyclone right here. So areas, as I said, in front, right at, behind, in front of the cold front, behind the cold front, everybody's going to be having different weather. And again, these things are most dominant in the spring because that's when the temperature contrasts are the most. And this is what they look like on a satellite image. Here's that circulation. So here's the warm front out here. Here's the cold front. And there's the cold air behind it. Notice that we see nothing back here. That means high pressure, cold air. This is where some occlusion is taking place. But as we have this circulation, now I got my arrows all screwed up, but as we have this circulation, notice that everything is converging into that center of lowest pressure. And when air converges, the only place it has to go is up, and that's when we get cloud cover and whatever rain or snow might be coming from those clouds. Here's another system that's developing here, but this section of the country is under high pressure. All right, so let's look at what happens here. Here's the CP air coming down. All the arrows indicate the direction that the air is coming from. Here's MT air, that's that warm air mass, and here's the MP air. So if we look at a cross-section of weather across here, across the entire thing, this is what it's like. Cooler air mass out here, MP air, cool air mass. Here's the warm front showing the cirrus clouds here, thickening up into altostratus clouds and nimbostratus clouds. Then here we are in this warm sector showing no clouds, but hey, what do you think would happen if there's moisture here? We're going to get clouds that form, and we might even get some thunderstorms in this region if that's the case. But let's just look at it as warm sector right now. And then here's that cold front marching in, forcefully pushing that warm air up, so giving us those cumulonimbus clouds. And after that passes, we're in cold, dry air, high pressure, cold temperatures. Here's another view. Here we've got an occlusion taking place. I don't know why they're not showing it with a purple line, but we got a little occlusion going on here. Here we have the warm air mass back here, cold air mass back here, and look at these little station models. The air, remember we talked about how these are locations and we can put all kinds of weather around these. For now, we're just looking at the direction that the wind is moving and the speed of the wind, but the little sticks on the station models are in the direction that the wind is coming from. So the wind would be coming from the northwest here. Here it's still slightly northwest. Here it's a little bit from the southwest, but it's all coming from kind of this direction. What's the wind direction here? This would be from the southwest. And the wind direction here is from the south to, it's really hard to write with these things. I need one of those pens. I just bought one of those Logitech crayons for writing on the iPad, and I'll be doggone, they sent me the wrong thing. They said that it would work on the model iPad that I have, and it doesn't. So that sucks. And then here, wind is coming in from the east. So it's all converging in here, and this shows up here, the occlusion, and you can see what happens. That cold air is caught up to the warm air, and it's pushing that warm air up. So there's going to be cloud cover and unstable weather associated with it. Snowstorms, rainstorms. But let's pay attention to what's going on here in this cross section from A to B to C to D to E. Every one of these locations are going to be experiencing different weather because they are being influenced by different parts of the mid-latitude cyclone. Out here, and we could do a weather forecast based on this. Out here, the temperature is going to be cooler than it's going to be as the warm air is moving. So cirrus clouds out ahead of the warm front, thickening up to cirrostratus, altostratus, and then right here at the warm front, nimbostratus clouds. And as this moves along, A will eventually be experiencing these conditions, but right now it's probably cirrus clouds here and cooler temperatures. At B, at point B, we actually have rain falling. And again, the warm air masses move fairly slowly, so these people might be getting rain for 2 to 3 days. Then that passes, and now these areas will be in this warmer sector. Right now, C is in the warm sector, so the wind is going to be from the southwest, warm temperatures, clear skies. D is suffering through violent thunderstorms, maybe even tornadoes, but they're short duration. So they can look forward to the passage of that cold front and now they're going to be experiencing the weather that E is experiencing right now, which is cold air, high pressure, clear skies. That will eventually be over D. Depending on the storm track, it will also eventually happen to C, B, and A. If the storm stays moving the way it is, then A will get the rain here, then the warm temperatures here, then the thunderstorms here, and will eventually be in the colder air as the cold front passes. Again, it's changeable weather. So here's another one of these mid-latitude cyclones on a weather map. This is the warm front here. This is that pocket of warmer air in the middle, air being cranked in from the Gulf this way. This is this colder region of high pressure, clear skies in here, and this is where everything's converging over here, and we've got probably, could be at this time of year, snow or rain. All right, I won't confuse you with that. But more, look at how much of the country is under high pressure here. All right, so that's where I'll stop for today, and we'll look forward to hearing about tornadoes and hurricanes and thunderstorms next time. See you later. Bye-bye.